Okay, let's get started. So far, my battery has increased over the last 10 minutes. I think that's good. Okay, let's recall from last time. Last time we learned the fundamental theorem of calculus, part 1. Which said that, so if, let's say we have capital F of X equal to the integral from A to X of F of T dt, then the theorem says that the derivative of this function is equal to little f of X. So in other words, and this is what the version that was written on the cake, we have d dx of the integral from A to X of F of T dt. This is equal to F of X. Okay, are there questions about this? So today we'll do part 2 of the fundamental theorem of calculus, and I don't have a cake for part 2 because part 2 is not as momentous. I don't think it's just a corollary of this. So here's part 2. So this says, so if f is a continuous function, on some interval from A to B, then this says the following. So it'll tell you how to compute the definite integral from A to B. So it says the integral from A to B of f of X dx is equal to, so all we need to do is take capital F of B minus capital F of A, where this capital F is any antiderivative of the function little f. Okay, so if I think of any antiderivative for the function here, then I can just calculate the definite integral by taking capital F of B and subtracting capital F of A. Let me make this minus sign a little bit clearer. Okay, are there questions about the statement? So we're gonna prove this statement, and it'll just be pretty much straightforward from the fundamental theorem of calculus part 1. And then afterwards, we'll use it to do a couple of examples of calculating definite integrals. Okay, so let's do the proof. So from part 1, I have a favorite antiderivative, which is the integral from A to X of f of t dt. Okay, so I'm going to call this capital G of X. So I'm going to let this be this function. Okay, so part 1 of the fundamental theorem of calculus tells me that G of X is an antiderivative of f. So we know that G prime of X is equal to little f of x by the fundamental theorem of calculus, part 1. Okay, so what I need to show is that if I have any antiderivative, capital F, then the definite integral is computed this way. So I'm going to let capital F be some antiderivative. Okay, so if capital F and capital G are both antiderivatives of little f, how are they related? Yeah. Yeah, so they can only differ by a constant, right? If they're both antiderivatives of the same function. So we know that f and g must differ by a constant. So I can write capital F of x is equal to capital G of x plus some constant. And this is true for all x's in the interval a to b. Okay, so now I'm gonna look at this equation and I'm gonna plug in that equation x equals a and see what happens. And I'm also gonna plug in x equals b and see what happens. So if I set, let's call this equation 1. So if I set x equal to a in equation 1, I get that f of a is equal to g of a plus c. So now I'm going to be able to solve for what this constant c is supposed to be. So let me write out what g of a is, because we said that g of a was the integral from a to x of f of t dt. So if I plug in a into that, I get the integral from a to a of f of t dt plus c. Okay, what is the integral from a to a of f of t? Yeah, this is just going to be 0 because we're starting at a and ending at a. So here I get 0 plus c. So this tells me that c is equal to f of a. So now I'll just going back to equation 1, I'll replace c with f of a. Okay, are there questions so far? Questions with this calculation? Okay, so now I'll go back to equation 1 and plug in x equals b. I'll just do this on the right portion of the screen here. So I'm going to set x equal to b in equation 2. And then I get f of b is equal to g of b plus f of a. And now let's write out what g of b is. So I have f of b is equal to the integral from a to b of f of t dt plus f of a. And now if I just rearrange this equation, then I get the conclusion that we were looking for. So I have the integral from a to b of f of t dt is equal to capital F of b minus capital F of a, which is what we wanted to show. Okay, so that finishes the proof of the second part of the fundamental theorem of calculus. Are there questions? So basically now, like, this tells me if I want to compute some definite integral, the integral from a to b of something, all I need to do is find any antiderivative of this function, and then plug in b and plug in a and subtract those two numbers. So it's pretty good, right? Like a week ago, we had to take a limit of sums of areas of rectangles, and it was like, we did like one by hand, but it was like huge pain. So this is like, it's pretty good. It's making our lives a lot easier for computing definite integrals. Okay, so let's do some examples. Let's evaluate the integral from -2 to 1 of x cubed dx. Okay, so there's like two steps. One, we have to think of an antiderivative for x cubed, and then we have to evaluate, we have to plug in 1 and plug in -2 and subtract those two numbers. So take a minute to think about what a derivative, or sorry, an antiderivative for x cubed is. I'll give you like a few seconds to think about this. Okay, what's an antiderivative for x cubed? Yeah. Yeah, exactly. So x to the 4th over 4. Yeah, I think this is the most natural choice, right? Of course, we could add a constant if we wanted to, but there's no need. So we just get x to the 4th over 4 here. Are there questions about that? So if you're asked for an antiderivative for something, you can always check your answer too. So if you take the derivative of this, then you should get back the original thing. And we can see here, like, if we do take the derivative of this, the 4, so using the power rule, the 4 will cancel this 4 and we'll just be left with x cubed. Okay, so that is x to the 4 over 4. And then for the part 2, we just need to plug in. So I'm gonna do, so we'll have, let's see, we're plugging in at 1. So we have 1 to the 4th over 4 minus -2 to the 4 over 4. So we can simplify this. So we have 1/4 minus 16 over 4. So then we're just left with -15 over 4 for the answer. Okay, are there questions about this calculation? Okay. So, okay, sounds good. So let's do one more. Oh no, I'll do some notation and then an example. So here's some notation that's often used for the evaluation step. So you can write, so if I have my antiderivative f of x, people will do like a right bracket, like a large right bracket like that, and then write a at the bottom and b at the top. And this is just, this means plug in B, and then subtract what happens when you plug in A. And I would just read this as like evaluated at. So I wanted to say this whole thing, I'd say like, f of x evaluated at B and A or something like that. Yeah. Yeah, it's the same. Yeah. But sometimes like you'll think of what the antiderivative is, and then you want to just like as a step say, okay, now I'm gonna evaluate that. Okay, so let's do another example. Let's compute the area under the graph. So let's do y equals cosine x from 0 to pi over 2. Okay, just so to draw a picture for this. If I start at 0, cosine is 1, and then at pi over 2, it's 0. So this is like this portion of this thing. We're going to calculate this area. Do you have any predictions or expectations about what that area will look like? Or maybe not. I don't know. I guess like I might expect that it would come out with like a pi or a square root or some weird numbers involved. Maybe pi over 4. Oh yeah. That's really good. It's actually, yeah, I kind of drew it looking like a circle here. It's not quite, yeah. Okay, so let's calculate it. So this area is computed by the integral from 0 to 2 pi of cosine x dx. So what's an antiderivative for cosine x? Yeah, so we'll have sine x. And then here I'll use the notation. So sine x evaluated at 0 to 2 pi. Like that. Okay, so let's compute this. So we get sine of, or sorry, this should be pi over 2. Everywhere. Okay, so sine of pi over 2 minus sine of 0. Okay, what is sine? Let me scroll up a little bit. What is sine of pi over 2? Yeah, so you can just picture, I always have to like imagine the unit circle in my head and think about the sine is the y coordinate and you have pi over 2, so that's going to be 1. So you have 1, and then what is sine of 0? Yeah. This is just 1, and then it's kind of surprising, like this just comes out to be an integer. You might think that it's like some wacky thing, but it's just, it has area 1. Okay, are there questions about this example? I'm gonna give you guys an example to work on right now, just to get a little bit of practice. So let's compute the integral from 3 to 5 of x squared plus 5 x cubed dx. So take a few minutes and work this out. If you finish, check your answer with your neighbor. Okay, do you guys need more time or? Okay. Okay, was there a pair of neighbors who got the same answer? Yeah. Okay, I didn't catch all that, but so hopefully people heard the okay, so you got 125 over 3 plus there was like a 3,000 125? Okay, sounds good. Okay. Did other people get agreement with this answer? Okay, sounds good. So we can check this. If you want to check this later, you can use a computer or something. So if you have you guys seen Wolfram Alpha before? That's like a good resource for computing integrals. So if you wanted to, you could type this into Wolfram Alpha. It's like an online calculator, but it has a lot of has like more power than a regular calculator. Okay, so let me just summarize some of the information from the two fundamental theorems of calculus. So you can think of the derivative and the integral as being inverse processes in the following sense. So the first fundamental theorem said this, so it said d dx integral from a to x of f of t dt equals f of x. So you could think of this as saying that the derivative of the integral of a function is the original function. So the derivative of the integral of a function is f of x. And of course, you have to be a little bit careful with this because of like what the bounds of the integral are. And then the second one said that the integral from a to x. So I'm going to write it a little bit differently than I wrote it the first time. You can think of it as saying that the integral from a to x of f prime of t dt is equal to f of x minus f of a. So this in some sense is saying that the integral of a derivative of a function, so here you have to evaluate the function of the two bounds. So the integral of the derivative of f is f evaluated at those two bounds. Stick a variable in there. Okay. So because of this, it's going to be useful to have notation for talking about antiderivatives. So far, we've sort of just been calling the antiderivative of a function the capital letter of whatever the original function was. But we'll make some new notation for antiderivatives. So I'm gonna say, so let's let f be a function. Then I'll write an integral with no bounds. This is gonna stand for the general antiderivative of f of x. So I'm gonna let this symbol denote the general antiderivative for f. So recall that the general antiderivative is when you find one antiderivative and then you add plus c to stand in for sort of like all of the different ways to add a constant to that function. So like this thing is representative of a family of functions, which is the set of all antiderivatives of f. And this is called the indefinite integral. So I'll make the note that the definite integral, the integral from a to b of f of x dx is is a number, right? It's going to be like one number. And the integral, the indefinite integral of f of x dx is a family of functions corresponding to the set of all antiderivatives. So this is like a collection of functions. Okay, are there any questions about this notation? For this definition. So we'll do some examples to see how this is used in problems. We're good. Okay, so let's do some examples. So for example, the indefinite integral of x squared dx. So this is just the set of all antiderivatives for x squared. So this will be x cubed over 3 plus c. Does that make sense? So let's do a few more examples. So the integral of sine x dx, what would this one be? Yeah, I'm hearing people hearing some whispers. So we have negative cosine x plus c. So, oh, this is not very legible. All right, so with this one, the only thing to remember is that when you take the derivative of cosine, you get minus sine. So we have to add a negative in front of there to get the right thing. Okay, and then you have rules for this as well. So if we have the integral of x to the n dx for n not equal to -1, then we get x to the n plus 1 divided by n plus 1 plus c. So at some point we had like an entire table of antiderivative rules, and you can basically just rewrite all of those now using this integral symbol. And there is a table in the book that lists all of the formulas with the integral. So here's like another example. We also have secant squared of x dx is equal to tan x plus c. And then there's, yeah, I'll say there's more in a table in Stewart. Okay, are there questions? Let's do another example, a more involved example. So let's compute the integral of 10 x to the 4th minus 2 secant squared x dx. And I'll give you guys like 5 minutes to think about how to do this, and then we'll do it together. Okay, let's go ahead and do this example. So the first thing that I can do is break this up into two separate integrals, one for the first term and one for the second term, because we have a sum and difference rule for antiderivatives. So this is equal to the integral of 10x to the fourth dx minus the integral of 2 secant squared x dx. And then I can also, there's also a constant multiple rule, right? So I can pull out those two constants. So this is 10 times the integral x to the fourth dx minus 2 times the integral of secant squared x dx. Okay, so for this first one, integral of x to the fourth dx, what is the antiderivative for that part? Yeah. X to the fifth over 5. Yeah, sounds good. So we get 10 times x to the fifth over 5 minus 2 times this other one. So what is the integral of secant squared x dx? Yeah. Yeah, so here we just get tan x. Okay, and then what am I missing? Yeah, we need the plus c, right? So you might be wondering, like, why don't we have plus 2c's? Right, because maybe I would get one for this integral and one for this integral. But if you add two constants, you just get another constant. So all of the possibilities are still represented by just having 1 plus c. Okay, are there questions about this? Okay, let's do one more example. Okay, so now we're gonna have a particle. And it's moving along a line, and we know a function for its velocity. So a particle moves along a line with velocity at time t given by the following equation, or the following function. So v of t is equal to t squared minus t minus 6, and this is in meters per second. And then we're asked to find the displacement at time t equal to 4. So the particle is moving with some velocity that might be positive and negative, and then we have to find its total displacement. So how much does its final position differ from its initial position at time t equals 4? So I'm going to let S of t denote the position of the particle at time t. Okay, so if S of t is the position of the particle, then the derivative of S of t is going to tell me how fast it's moving, right? So the derivative of S of t is going to equal v of t. Does that make sense? So So S prime of t is equal to V of t, which tells me that S of t is an antiderivative of V of t. So what that means is that if I want to find the total displacement of the particle, that's going to be given to me by S of 4 minus S of 1, which by the fundamental theorem of calculus is the integral from 1 to 4 of V of t dt. Yeah. Good question. I don't know. So I think I just messed up the example. So I have to put 0 in here. I think in the question I didn't say, so let's say, the displacement, yeah, because we didn't give a starting time, right? So let's say the displacement between time t equals 0 and time t equals 4. Yeah. Thanks for that. Does that make sense? Was there another question? One of the same question. Okay, other questions? Okay, so let's compute this integral. So this is the integral from 0 to 4 of, I'm just plugging in V of t, so I have t squared minus t minus 6 dt. And then this is going to be equal to, so I'm going to take the antiderivative now. So t squared is going to give me t cubed over 3. Minus the t part is going to give me a t squared over 2. And then the 6 is going to give me minus 6t. And this needs to be evaluated from 0 to 4. Is this making sense? Okay, so then I'll just plug in 4. So I get 4 cubed over 3 minus 4 squared over 2 minus 6 times 4. And then, so that's my 4 contribution. And then we're subtracting what happens when I plug in 0, which is just going to be 0 in this case. So then our final answer is whatever this simplifies to. So what is 4 cubed? 64? 64 over 3 minus 16 over 2 minus 6 times 4. Let's not bother with the simplification. We can just leave it like this. That's our final answer. Okay, are there questions about this example? Okay, so on Wednesday, so we have a midterm on Thursday. So on Wednesday, we're gonna do review for the midterm. If anyone has ideas about what the most helpful format for that would be, feel free to let me know. Just like come tell me right now after class. And yeah, I'll see you guys on Wednesday.